So the conduction equation we usually call is conduction. So we first, like in the fluid dynamic, we need to consider a control volume first. So the control volume maybe look like this. Okay, so at different x, let me point out the axis first. So this will be x, y, z. Okay, and unlike the chapter 1, it's more complex. We have a heat generation inside of the control volume. So let's take it down. This is a heat generation. Usually we call it Q gen, and this is volume, cubic volume watt. So the heat generation always is volumetric phenomena. 它是一个体积的概念，从体积开始散热三维的体积的概念散热，所以你可以看到它的单位是瓦除上 cubic meter。Okay, so now if we have a heat, this is in x direction, this one, and this is y. This is z, sorry, and this is y. And if we have a q here, then it's like fluid dynamic. You have that x, delta x, delta z. Okay, so if we only take the x direction to do the driving, so we can, the qx, the qx delta x, we can read it down like this, equals 2x plus partial qx along the x. Then I won't write it down the rest of it, but you look like this. So far, okay? It's quite similar to the fluid dynamic. So still, based on the first law of the thermodynamics, so the energy conservation. So the energy come into the system minus the energy leaving out the system, and plus the generation. This will be the energy change inside of the system in certain time. So this will be the rate of the conduction at x, and this will be the conduction, also the heat conduction rate at the delta x position, x plus the delta position. And this is the energy generated inside of the element. And this is energy change content inside of the system or element. Okay, and then we can switch into another form. Because we need to tie the area, so I just quickly write down. E in is here, minus this is energy out. Okay, here is volume. Because we already mentioned the heat generation is in the volumetric phenomena. So the Q, small q, needs to time the volume will equal to the watt it has. And it equals to the internal There's a lot of similarity between fluid dynamic and heat transfer we'll describe later. There's a lot of equation that you can relate it to it. Okay, then we further divide the U, the internal energy. If you remember, that will become the N times the small u, right? 单位质量乘上小 u. Then the N can become low dx, dy, dz, low v. Then the U can become heat capacity, no, not heat capacity, specific heat and times the temperature. Okay, so now every equation have the dx, dy, dz. Then the equation could become slightly simplified. Okay, take a look at this first. So first we can try to the qx dy dz and the qx delta x dy dz, then we can like minus it. So what we get is only this term, okay? Just write it down. Let's take the minus point out. And then we take out the common part. the CP won't change, the density won't change, the volume won't change. So the differential is only donate on the temperature. That's the reason we put it here. Then we use the Newton cooling law. And then put it back into the equation. It will become the PDE. That's the heat equation. You might find that very similar to Navier-Stokes equation. If you remember this. This D is derivative.有没有看起来很像？我们把 K 拿出来的话 ，if we consider K is the constant, that will become mu。然后这边散度，然后后面重力项 gravity 压力项，这边是 heat generation 等于时间的变化量。 这是等于速度的变化量。Okay, so if we take a look at the equation closely, so you will find the full heat equation. It will be 3D. Of course, we drive it in 3D, and this is unsteady. So either the K or the temperature propagate at a different position is at a different speed, and then there's a variation in terms of time. And the K we put it inside of the equation, which means the K is the function of the x, y, z. Which means the K value inside of the material is different. K 各处的值在你的材料当中是不一样的因为这是最完整的。这个最完整能解的三维，然后 unsteady， 然后 K 的值是一个变数，然后 with heat generation. So those are the full equation of the conduction. Okay, So if life is easier, let's make it slightly simpler. For example, the first one, if k is constant， 我们先看第一个最简化的做法。所以如果 k 是 constant 的状态之下， So if k is constant, so we can take out the k from the evaluation term. 我把 k 从微分项拿出来，然后我再把这个常数 low c 移到 k 的下方，我把所有的常数都移到同一边。Okay, so those are if the k equals to the constant. So if we return into the vector form from the original one, we can return like this. Maybe it's easier to remember. Oh, 如果把它写成向量的方式的话，把它改成这样写也可以。Okay, so why are we going to put all the parameter on the left-hand side? Because we want to introduce something very important. On the chapter 1 we already mentioned, you probably already forget on page 62, this one. This is called thermal diffusivity, 热扩散系数 alpha. So we see it again on the chapter 2. So the alpha, the definition of the alpha actually means how the heat, the ability of the heat going to penetrate the surface versus the surface going to absorb the heat. 从它的比值上你就可以看到嘛，就是上面是跟 conduction 有关。那下面是 low c，c 是 capacity， 就是吸热的那个能力。OK， 所以它的比值叫做热穿透。对上热吸收。Okay, so what does mean if the K is really big? Means if you have a surface, then you have very big K. Means all the heat you transfer from one side to other side, the most of the heat going to transfer it. So no such energy inside of the surface. 可以吗？所有热都传出去，完全不停留。那什么是 low C 很大 ？low C 很大的意思就是。我这边传进去，只有很少的东西传出来，那这个就叫做 low C 很大，我所有的 energy 都被存在我的系统当中。那这样的比值，我们就用这个 alpha 来去描述它。 this is not a dimensional number, so it has a unit. Okay, let's drive the unit a little bit. So the k equals to n squared c. Okay, easier. Not squared, sorry. Low c, so kg meter square. C is the joule divided by kg per k. This is okay, so let's have some discussion. So what does mean the alpha is extremely big? Which means the system is at a steady state. So all the heat is going to propagate. Doesn't matter. There's no direction difference, so it's easy to propagate. 多少热进来，我就多少热出去。所以 alpha 很大的时候，如果你算出来很大的话，这个题目直接用 steady state 去解就可以了。Okay, so if under the steady state, then if we have no such heat generation inside of your system, so the heat equation will become like this. 现在 steady state 的状况之下，你没有 heat generation， 然后这个状况呢，你就只剩下这边的项，这边没了，然后 steady state 这边也没了，所以变成这个值。这个叫什么 ？Laplace equation。就是困扰你们公数很久的，为什么要学 Laplace equation？ 只是在热传学会看到。这是 no heat generation。But what if we have a heat generation? Then we need to leave the term, right? Then we move to another side. This 这个旁边有一个这样子的变数。这个是什么 equation？ 在公数当中 ，Poisson equation 啊。Okay, so all the mathematical solution is already being told. 直接用在公数的时候解的方程式去求解就可以了。我会带大家算过一次，所以不要担心。Laplace 应该是最简单的，因为2阶等于0的话，就表示它的 t 的 propagation 大部分都是线性，要么是线性，要么是常数。就是如果从物理的意义上面来看的话。Maybe we come back to the slides first. There's not much time left. So as we mentioned, the temperature is the scalar quantity, and the heat transfer is vector quantity. So that's a three-dimensional. So you need to drive it x, y, z, and on circumstances is a cylinder coronidae or is a spherical coronidae. There will be different form that will be discussed in next chapter or later content. Yeah. Then the steady means the partial t equals to 0. It doesn't matter it's a position or it's a time or temperature, and the transit means it doesn't equal to 0. Okay, it's quite obvious. And something we talk about with the length system, which means it's variation with time only, but not within the position. 它的温度变化只跟时间有关，跟位置无关。So, for example, a relative small metal ball compared with a big brisket in your oven, then the small ball will consider as the length system, but a frozen brisket isn't. 像冷冻的牛胸肉，你要拿去烤它的时候，它就不能 consider 它是一个 lamp system， 因为它里面是冰的，然后你外面烤它，慢慢温度传进来，它就不是 lamp system。但是一颗金属球，我们可以把它当成 lamp system 云团。这个我们后面还是会再讲到。然后怎么判断这个东西是不是云团，有一个非常重要热传学的无因次项，跟雷诺数一样重要的，也会讲到。Okay, so the textbook quickly touched the concept of the lamp system as we just mentioned. So if it's a metal ball, then it's considered a uniform all the time during the heat transfer process. But the roast beef or brisket put into the oven isn't. Okay. So just by looking at those texts, you can realize the lamp system will be easier way to solve the equation because it's only variation of time, not in the position. Okay. So of course it's a multi-dimensional heat transfer, one-dimensional, two-dimensional, three-dimensional. But sometimes you can simplify your scenario. For example, if you have a pillar, then you want to know the temperature propagate along the pillar or a heating cylinder, then you probably can consider in the x direction there's no temperature variation 在你的镜像或者是你的那个柱子的这个 z 轴，可能它的 temperature 不改变，我们就考虑它不同面的热传进去。So you can reduce your three-dimensional into two, or like for example like this, it's only a one window at certain position of the house, then you can consider there's a primary direction of the heat transfer. Then you can neglect the other direction. Okay, so by driving those kind of heat equation, they review Fourier law of the conduction a little bit. Then mention the heat flux vector is always normal to the isothermal surface 你的热传永远都是正交于你的等温表面，然后所以你 all the heat flux vector can be divided or resolved into three dimension x, y, z， 所以你的热传就有三个方向 x, y, z。那课本上面的推导，我觉得有一点点复杂，你们可以试着看一下如果考试有考，或是以后有要去考其他研究所会用到的话，两种推导方式都可以。你可以看一下课本课本in the textbook is also start from the one-dimensional surface and then slightly develop into 3D and then consider element as well. Then the rate of the heat conduct at x and minus the heat conduct at x plus the delta x will and plus the heat generation will equal to the energy change inside of the element. Okay, 前面大概一样。Then it divide. You can see the blue one. Let's go to the blue one. So the delta E element equals to the next second or next time point t plus delta t minus the t equals to n specificity, and then times the temperature change, and then you got those things. It's quite similar from what we divide, but but I found it's really hard to read, so that's the reason we reconstruct the process. Okay, so it's also start from the conservation of the energy, so you can see what you get here. 你的 energy in 跟 out， 然后它把它整合在一起，然后你的heat generation is in the volumetric phenomena， so 你的 A 乘上你的 delta x， 所以它是一个体积的概念。然后跟我们刚刚这个 E element 内能所传达的东西也一样。然后接下来333，然后 so consider when the delta x is approaching to 0， 非常小的移动位置，跟 the time limit equals to 0， 在这个时候它用这个这什么？我忘记它的，反正就是极限的展开这样子，然后它就会变成趋近只有这个值，然后下去带。So you can have a one-dimensional heat cut-down-shear equation from a large plane， 完全一模一样的东西。So this is only one-dimensional. Okay, then we recall something from, okay, so it's page, not 62, it's page 56, the thermal diffusivity. Then further discussion, if there's a steady state, or there's no generation, or there's a heat generation, then it will become a different kind of equation. So what we didn't talk about is if it's non-steady state but without generation, then you still need to let the temperature change term here. But usually we discuss with the steady state and no generation. This will be the Laplace form. Okay. I think we still have 10 minutes, so let's see 12 minutes here. Let's see an example here. So this should pop in onto your PDF file. So I will switch off the projector later. So let's consider a wall, which also generates the heat inside, or object, doesn't matter. And there's a heat generation. The thickness. I will first use the label, then later on you can put the number you want inside. And as far as we know, the temperature distribution Tx equals to A plus Bx plus Cx squared. 像速度的 profile 一样 ，temperature 的 profile， 它从这边传到这边的时候长的 样子。那我们前面 conduction 讲都是 linear， 那接下来就是比较困难一点，它可能是一个曲线的一个状态。OK， then we have a heat. Of course, we have a heat transfer from left hand side to the right hand side. So, body Q in, Q out. So we first write it down, the heat equation. Then always remember it's volumetric phenomenon. So it will be small q times the A times the L. Sorry, I didn't mention the area. I don't have other color. The surface is area. So first we can start from the Fourier law. The Q equals to minus K A delta T delta X. Then minus K A will become B plus 2C. OK， 好，我们直接做一次微分。Okay, so if we want to know what's the Q in and Q out, there will be Q x to 0, Q x to L. 好吗？直接带进去就好了。哦 ，sorry， 防选项不见了。Then if you want to know the temperature change along the time, then write it down the heat equation again. OK， 两次微分。Okay, so you can put it those number into the questions. Give you the number I calculate. So this will be roughly this will be so if you want to see how the system have how many energy inside of the system, this will be, yeah, you can calculate. So the minus point means the temperature is going to propagate out to the element. And you will find the Q in didn't equal to Q out. As we mentioned, if it's in the steady state, every surface, every cross-section, the heat propagate should be the same. But here, the Q in didn't equals to Q out. So which means this is the unsteady system. Or you have the Q generation inside. Then there's a minus point here. It means the every second how many temperature going to drop. 哦，慢慢的在温度下降，很低啦，4.7乘以10的-4次方度 C 每秒的下降。Okay. Although the temperature profile I'll draw looks like this, but sometimes after the calculation, if you have the temperature profile, then the number will tell you what exactly is going to emit the heat, not emit, transfer the heat or to absorb the heat. Okay, so if there's no further question, we will stop here and dismiss the class.